Welcome friends, Igor is here, and in this video we will define linear combinations of column vectors and use them to advance our understanding of solutions to linear systems. In this lesson we will define a linear combination of column vectors. Notice that linear systems can be represented as linear combinations of the columns of the coefficient matrices, and prove that solutions to a linear system are the scalars in the linear combinations of the columns of the coefficient matrix that are equal to the vector of constants. Let's get started. In the previous video in this series, we defined two operations on column vectors: vector addition and scalar multiplication. Now we are going to combine these two operations to produce the notion of a linear combination. Given n column vectors of size m and n scalars, their linear combination is given by the following expression. We multiply each vector by the corresponding scalar in the list, and then we add up the resulting vectors. In other words, we take a list of vectors, we take a list of scalars, the number of scalars is the same as the number of vectors, and we combine them in this specific way to produce one new single vector. Here is an example of a linear combination. Let's take three vectors of size 6 and three specific scalars. We can form a linear combination of these three vectors with these three scalars, and if you compute the result of this linear combination, namely, you multiply each vector by the corresponding scalar, then you add all the resulting vectors, and in the end, you get one single vector, which is of the same size as the original vectors used to construct the linear combination. Now, let's keep the same vectors but change the scalars. This results in a new linear combination, which produces a different vector. Now you see that, for example, you can keep the same set of vectors, but you can change the scalars you use to produce linear combinations, and by doing this you can compute a lot of different linear combinations. Now I'm going to relate the notion of linear combinations of column vectors to linear systems. We already know that we can replace a bunch of equalities in a linear system by one single vector equality. But now we are going to take this one step further. We are going to take the vector on the left of this equality, which represents the left-hand side of the linear system, and we are going to split this vector into addition of several column vectors. I hope you noticed a pattern how we achieved that split. In the first column vector, we collected everything that is related to variable x1. In the second column vector, we have everything that involves variable x2. And in the third column vector, we have everything that involves the variable x3. There are three variables in this linear system, and that is why we use three column vectors. So we made use of the operation of vector addition. Now, let's make use of the operation of scalar multiplication. Notice that each of the three individual vectors has a multiple of the corresponding variable. So we can factor out x1 out of the first column vector, we can factor out x2 out of the second vector, and x3 out of the third vector. Notice that these are still the same vectors by the definition of scalar multiplication. In this case, we can think of these variables as scalars. So we converted this vector on the left into a linear combination of simple vectors. But three vectors that we have on the left-hand side are not just some random vectors. Here's why. If you look at the original linear system and you construct the augmented matrix of this linear system, you should be able to recognize that the vectors we have in this linear combination expression are precisely the columns of the coefficient matrix of the original linear system. Moreover, the vector we have on the right-hand side is the vector of constants of the linear system. The original linear system, which involves 3 equations, is equivalent to one single vector equation, where we have a linear combination on the left-hand side. Moreover, the variables in the original linear system are used as scalars in that linear combination. To solve the linear system means to find the values of the variables that satisfy all equations. In particular, in our new vector interpretation, it means that to solve the linear system is to find the values of the scalars x1, x2, x3 that make the linear combination of the columns of the coefficient matrix equal to the vector of constants. Let's formalize this observation in the following theorem. Suppose we have an m by n matrix A, and let's denote its columns, which we can think of as column vectors, by a1, a2 through an. So we're going to use the same letter as the matrix, but we will use the boldface font to emphasize that these are column vectors, to be consistent with our habit of using boldface letters to denote vectors. We can use this matrix A as a coefficient matrix to construct a linear system, and let's say we use some vector B as a vector of constants. Then a vector x of size n is a solution to this linear system if and only if the components of the vector x are the scalars in the linear combination of the columns of the matrix A that are equal to the vector of constants B. This is an if and only if statement, and therefore there are 2 separate implications for us to establish. In fact, this proof is nothing but careful change of notation of all the notions we already know. To help us visually see what is going on, let's write the linear system with A as the coefficient matrix and B as a vector of constants in its standard general rectangular form. Then column number j of the coefficient matrix A contains the following components. It's a1j, a2j, up to amj. This is a column that in a linear system corresponds to variable xj. And now let's observe that the ith component of the column vector aj is simply aij. We're going to use this observation in the proof. First, we are going to assume that the components of the vector x produce a linear combination of the columns of the matrix A that is equal to the vector of constants B. Then we need to prove that this forces the vector x to be the solution vector to the linear system. We are given a vector equality. Linear combination of columns of A is equal to the vector B. In particular, this vector equality means that these 2 vectors have identical components. So let's look at generic component number I of the 2 vectors. Our assumption is that they are equal to each other, and this is what this equality says. Now, let's translate what is the ith component of the right-hand side of this equality. Using the definition of the operation of vector addition, we see that it splits into the addition of ith components of these individual vectors. Now, we are going to use the definition of the scalar multiplication to see that each of these components is the corresponding scalar multiplied by the ith component of the vector inside. Now is the time to recall our observation from the previous slide. Component I of the column vector aj is aij. Finally, using the fact that multiplication of numbers is commutative, I'm simply going to change the expression slightly to help you visually see what's going on. If you look at the beginning, at the end of this long equality, you will see that it says precisely that components of vector x satisfy equation number I of the linear system, with A as the coefficient matrix and B as a vector of constants. But this holds for every I. Therefore, components of the vector x satisfy every equation in the linear system, and therefore the vector x is a solution to the linear system. In the other direction, we are now going to assume that the vector x is a solution to a linear system with A as the coefficient matrix and B as a vector of constants. In particular, vector x solves equation number I. Now, I am simply going to reverse our development from the previous slide. First, I'm going to use the commutative property of multiplication of numbers. Then, I'm going to use our observation about the components of the column vectors of the matrix A. Then, we're going to use the definition of the operation of scalar multiplication. Then, we're going to use the definition of the operation of vector addition. But now, if you look at the beginning and the end of this equation, it says that component I of vector B is the same as component I of the linear combination. And because it is true for all I, it means two vectors are equal. The vector B is equal to the linear combination of the columns of the coefficient matrix A with the components of the vector x used as scalars. And this is exactly what we intended to prove. We have demonstrated two implications, and therefore this completes our proof of the if and only if statement. If you found this video useful, please give it a like to help others discover this content, and subscribe to the channel to see more future videos. In the next video in this series, we will discuss the vector form of solutions to linear systems and how null spaces can be used to describe solution sets to non-homogeneous systems. I will see you later.